welcome to Live Science from the Creation Museum. We're here again in the Science Education Lab, and this morning I'm Mr. Roger Patterson, and I'm joined by Dr. Jennifer Rivera. She's here today to be my co-host and help us with the comments.
An assistant.
We'll be giving a minute here for everybody to jump on for all those notifications to go out. But while we're waiting for that, why don't you just tell everybody what you do here at the museum?
Yeah, so I am the Education Content Administrator, and I do oversee the programming that we have here at the Creation Museum. And so we do have several types of free programs for our guests. We also have Explore Days for our students and Explore Camps. And so we actually have 4 camps coming up this summer, and registration is open for those. And so we're excited about that.
So we've got lots of workshops that happen here daily when the museum's open, and different types of overnight programs, camps, all of those types of things, and lots of opportunities to learn. And we're doing these types of broadcasts during this time where the museum's closed to give families an opportunity to engage some of this content. Hopefully show you how God has created the world in a very orderly way, a way that's systematic, easy for us to understand so that we can do science. And in fact, that's one of the foundations for a scientific understanding of the world, that God has created order in the universe, and we can study that order and understand how He's created it. And that gives us a foundation for science. If things were random and naturalistic accidents all around us, why would we expect that things would be uniform and continuing on? Okay. All right, well, let's go ahead and jump into our topic today. So today the title is Electrified Chemistry. So we'll be talking about the subject of electrochemistry and dealing with these things. So you can see lots of paraphernalia spread out here that we'll looking at today. We're going to be trying to follow your comments and answer a few of those questions as those come in as well. And we'll get started here talking about electrochemistry. So you may have noticed there's an odd thing here. No, it's not going to explode. Nothing's going to happen.
Wait, Roger, you don't have your safety gear on.
Oh, well, okay.
Don't you need goggles and gloves?
Good question.
Safety things.
Earlier, when I was preparing things and working with some stuff, I was wearing my gloves, I had my safety glasses on, all of those pieces. Everything we've got out today is pretty stable. The most toxic thing we're going to be working with out of the container is some vinegar, so we're going to be all right. So we don't need to have our glasses on today.
Okay, that's good, because I don't want to get any damage to my eyes or something.
Me
so
either.
That's good.
Definitely not. We'll be careful with that.
Okay, good.
Okay, so back to our potato clock. If the power ever goes out at your house, all you have to do is get some that power. That's the basic principle here, right?
Now, wait a second. Are you trying to tell us that a potato is powering that clock?
Well,
really? Come on.
Well, if it was, we could do a scientific test. So if I take out one of these little pins right here, this electrode, it goes out. The power to the clock goes away. If I stick it back in, I've got a circuit there to complete it. So is it the potato that's powering the clock, or is it something else? We could do a scientific test to understand that. Let's try, rather than a potato, let's try it with an apple and see if the same thing works. And there we go. We've got power back to the clock. So it must not be the potato per se that's doing it.
Something
so it must be something else, something inside. So you'll notice here we've got these little wires connected in different ways. Some of them have black tabs and some of them have red tabs. Both of the red tabs, you might look at that and say, that looks kind of like a metal copper. And then the black ones that kind of looks shiny silver. You may not know what that is, but that's actually a zinc electrode. So it's not actually the potato that's powering these things or the apple, but it's the metals that are here that are giving us power. And on one, I have a black and a red connected, and on the other, I have a black and a red connected. If I disconnect any of those, or if I reverse the position of these, I'm going to lose that power. There's not enough power there to power the clock. So it's set up in a very specific way that allows that power to flow and create enough electricity here to power the clock. Okay. So when we think about these, we think about the concept of electricity. Electricity is just the flow of electrons. Now you probably know from basic chemistry, basic study of science, that every atom is made up of a nucleus, which has positive protons and neutral neutrons, and then out floating around it are electrons. So we try to take advantage of those electrons moving around the outside of atoms to create electricity. And this is a phenomenon that's been known for thousands of years, how these things work, but it was really defined back in Italy in the 1780s by two guys from Italy named Volta and Galvani. And they had very interesting first names as well.
I wonder if that's where we get certain terms we use today when we talk about electricity.
Oh, probably.
Could be.
So the volt, which is our standard measure of electrical current, comes from Alexander Volta. And galvanizing, a process we use in plating metals, is from Galvani's name. So yes, lots of scientists find their names used in different ways. Ampere and ohm are other names we use associated with electricity as well. Okay, so we're going to run some tests and think about the way different metals can be used to create different cells. So over here I've got a bunch of different little sheets of metal, and we're going to talk about the electrochemical potential of these metals. So this is zinc, copper, iron, aluminum, and then I also have some nickel plate over here, a carbon rod, a graphite rod, and then some magnesium. Every one of these metals has a different level of electrochemical potential. So if you think about potential, if I hold something up in the air, it has potential energy to come down. We can think about that with electrons too. So electrochemical potential is how likely is this metal to lose its electrons inside of a cell, a voltaic cell. So we're going to use a substance you guys have around the house, this little beaker filled with vinegar. And the vinegar is important because it acts as both a source of hydrogen and an electrolyte. So it's a salt solution basically that allows electricity to flow. You may not know this, but water does not conduct electricity. Most people don't think about that, but water, pure water, can't conduct electricity. So we have to have an electrolyte dissolved in it for it to be able to conduct electricity. But that doesn't mean we shouldn't, it still means we shouldn't put electrical devices in our bathtubs and things like that, because there are salts on our body and other things that dissolve and make that water conductive. Even the tap water that you have is probably conductive. All right, so this vinegar is going to give us a conductive solution, and we're going to test a bunch of different metals and look at how they conduct electricity. And what we've got here, I've got connected a voltmeter, and this voltmeter is going to help us look at how much potential is created from that. So first we're going to start out with a carbon rod, which has practically zero electrical potential, and then a nickel plate. And when I put this into the solution, it's going to start what we call an oxidation reduction reaction, often called a redox reaction. And as the electrons are migrating, they're moving from the oxidized side, which we call the anode, which is the positive side, so that would be the carbon rod in this case, to the cathode, which is the negative nickel in this case. And when we look at a standard battery cell like this, you'll often see they're noted with a plus and a minus sign. And that plus and minus sign is what tells us which way the electricity is flowing. So the anode, the positive side, and the cathode, the negative side, that's the way, the direction that the electrons are flowing. So the electrons flow from the cathode around the circuit back into here. So in this cell, what we have is the nickel is creating 0.28 volts of electricity, 0.27. So let's switch out this plate and see if we can get a different result. So the iron...
You know, Roger, we have a good question.
Okay.
Someone is asking, well, what is zinc and what is nickel? What are they? Where do they come from?
Okay, zinc and nickel, copper, aluminum, all these things that we're looking at are just elements. So these are things that God has created as part of our world. So we would find these in all types of different rocks and ores, and then we refine them to purify them so we get pure metals. So metals we describe in chemistry as substances that are malleable. They can be shaped like a mallet. If you hammer them, they can be bent and shaped. They conduct electricity well, And that's demonstrated here in this example. Okay? So iron, common metal you probably have around the house, if we put this in, it has an electrical potential of 0.74. So it's very similar to the nickel. And we can see the reading there on the voltmeter. We move to something else, something a little more. With the zinc plate, you can see that jumps up to 1.2. So we would say that zinc has a higher electrochemical potential because it creates more voltage as those electrons are flowing. So let's ask you kids to make a prediction. What do you think is going to happen if I take off the carbon rod and I replace it with another zinc plate? Okay? If there has to be a difference between the electrochemical potential of the two plates, is there any difference between the electrochemical potential of this zinc and this zinc plate? Let's find out. And we're getting a tiny little bit of reaction because there is some hydrogen exchange going on inside those, but virtually no voltage. So there's no difference. That's a property God has created in the world. Zinc is always zinc. It's got its common properties no matter where we find it. If we went to another solar system or another star system even, we would find these properties of elements are consistent all through the universe. And that's another example of how God's created everything in a very uniform way. Any other questions coming in yet?
No, nothing yet.
Okay. All right, so if we think about these different metals, rather than just using the carbon rod, we can actually create a cell using two different metals. So if we use the zinc and the copper, and we put those in, they're going to have a potential of about 0.96. So that's a little less than what we saw when we had the carbon rod in. So that means copper must have some type of electrical potential itself that it's contributing to this cell. What's going to happen to the voltage if I reverse the leads? If I put the black wire, the cathode, and onto the other side. If I switch these, what's going to happen to the flow of electrons in the meter? The value is going to stay the same, but it could potentially, depending on the meter, is going to show up as a negative value. And if I swap out something with a little, go back to our carbon rod. Okay, we have zinc at 1.15, and then the copper, if I use that as my ion, coming in at 0.9. So we know that there's a change in the amount of electrical chemical energy that's flowing back and forth between these things. And all of those different metals that we can use, if we try aluminum, we're going to get a different value there, down to 0.38. Okay. And nickel, if I can pick that plate up, get the value of 0.86. So all these are creating different types of voltage. Magnesium, got a little ribbon of that here. That might start bubbling inside that acid. Okay. This one is so reactive with the acid, if you can get the camera in there tight, you can actually see little bubbles forming of hydrogen gas bubbling off of here. Now, if I were to use this in a battery, it would be creating a lot of hydrogen gas. Bad news about hydrogen gas, it explodes. Okay?
I remember something that happened in our history
involving
hydrogen gas.
Yes, they used to fill giant blimps with hydrogen gas, and the Hindenburg was trying to dock at a station in New York, and there was some type of electrical spark. It ignited the balloon and it exploded. So hydrogen gas being produced would probably be a bad thing. I wouldn't want to choose this magnesium for a battery because it'd be building up a lot of hydrogen gas, and then that could potentially cause an explosion. So we can take advantage of the properties of these different metals to be able to use them for different types of applications.
Yeah, and I bet that's why a lot of baking pans are made out of aluminum, and we use aluminum foil to cover things because it has such a low conductivity. So it's safe to use for things like that.
Okay, so any other questions coming in yet?
No, nothing much. Just lots of people tuning in from Michigan and South Carolina. Some people are saying it's really cool.
All
so they're
right.
enjoying
Okay.
what they're learning today. So lots of comments about how awesome it is.
All right, we're going to use this zinc acid reaction in the future to make another explosion. So we'll talk about that in the future. So let's think about things that you use every day that take advantage of this electrochemical energy. Now, it's not handy to have a cord attached to everything if you want to go out and do something away from your house or somewhere. Say we needed a GPS system to be able to guide us as we're hiking. Not real handy to drag a cord through the woods to have that connected to something. So these batteries and cells are the way that we've adapted this technology, taking what we know about these electrochemical cells and how these metals interact with one another in a beaker like this, and we've packaged them into little things like these. Now, here's a common misconception. We typically call these batteries, but technically this is just one cell. But this is indeed a battery. So we'll talk a little bit about the difference between a cell and a battery. A cell is just one unit of some type of electrochemical difference. So we've got some type of anode and some type of cathode metal that's interacting with and releasing those electrons as we flow through there. So if you were to cut open, go ahead and come on in here tight and let's take a peek at this. If you were to cut open a battery, something you should not do, I did this this morning very carefully with glasses and gloves on, you'll notice that inside of here you can see different components. This type of cell is called a zinc carbon cell. So here in the middle we have a carbon rod. That's the same rod I used over when we were putting that inside the electrical cell, a graphite or carbon rod. And then in this section here you have this black powder which contains zinc and ammonium chloride and a couple of other things that are embedded in here. So this is a reaction between the zinc and the carbon rod. So that's the same thing we do right over here in the cell if we put these two pieces together. And you can see we get a voltage there of about 1.15. So a zinc carbon cell typically produces a voltage somewhere around 1.2 volts. And that's going to happen every time we do that. So every zinc carbon cell that we get is going to work that way. Another name for this type of battery, as we typically call it, is an alkaline battery. So this is another misconception. A lot of people think that there is acid inside of batteries. And even if your mom told you don't touch that white powder that's on the battery, it's acid, that's not quite true. Now there are some batteries that do use acid, but these types of batteries we call alkaline. And if you remember back to our discussion of acids and base that we did last week, acids are one type of substance and bases are alkaline things are another. So this uses a different substance. It's an alkaline substance of potassium hydroxide. So it's got the hydroxide ion in it, not the hydronium ion. So it's actually an alkaline cell. So this cell, if we cut it open, it would look a little bit different, same basic concept, but it would have a little brass pin down inside of it and operate a little bit differently.
But should kids be doing this at home and cutting batteries open?
Absolutely not.
Definitely
this is
not.
something that I did in a very safe, controlled way, and you don't want to be touching these powders that are in here.
Right.
So especially if you get the white powder that forms if a battery kind of leaks or gets overpowered, we don't want to be touching those things. You can brush off the electronic pieces with a brush. Whenever I do that, I always put on a pair of safety glasses because if I'm brushing that stuff off with a brush, it's going to flick around and you can get that in your eyes. So be safe when you're dealing with those things. We don't want those chemicals in our eyes.
Oh, someone asked about fluoride. They said, would fluoride in water be a conductor? Because they often put, fluoride in our water. Right, to help with our...
Yes, that would be
hygiene.
one of the types of salts that would be found in water. Yeah. More common, we'd get the calcium salts and other types of things that are just present, what we call the hardness in our water. Okay, so other types of batteries that we have. This is a 9-volt battery, and it is truly a battery, okay, because inside of here are basically 6 small cells arranged in a certain pattern. So I've got this here to show you explain what happens with these different types of arrangements. So here I've placed 4 of these cells in a row. So we call this a series because it's positive, negative, connected like that. So these are just stacked up in a row like this. These are stacked with all the positives on this side. I guess flip that over, on all the negatives on this side. So this is all set up here, all in a row, so that all the positives are connected. And I've used this copper wire to connect them and just taped them together. So let's use our voltmeter. And get these things over here. And if I look at the red's always going to go to my positive end. Okay. That red is the anode end, the positive end, and the black is the cathode end. That gives me a voltage of 1.6 volts. Okay, 1.6 volts on an individual cell. So I want you to make a prediction. I have 4 batteries arranged here in a series. How many volts do you think that's going to create if I connect these wires here to these leads? Okay. The original was 1.6, and now I get a value of 6.5. Okay, so what's happening here? When we connect something in series, it actually adds the voltage of each one together. So if I take roughly 1.5 times 4, I get about 6 volts. So that's what this lantern battery is right here. It says it's a 6-volt battery. So if I were to look inside of here, I'd actually have 4 long cells that might look like something like these D cells stacked inside of here. And they're set up with positive, negative, so that they pass the current through there. And if I put 4 of them together, I get 6 volts. So what do you think's inside of this 9-volt battery? Okay. If they're basically the same thing, it's a 1.5 volt cell because it's using that basic zinc and manganese dioxide is the reducing agent in there. So if I have zinc and manganese dioxide, I get that 1.5 volts about. So I would need 6 of those little cells. So imagine, we call this a AAA cell. Imagine 6 of these stacked in here so that they were alternating in a pattern. And this little case just holds 6 of those. They're a little bit smaller because they don't have their outer case. So this is basically 6 times 1.5 gives us 9 volts. Okay. Other batteries you might have, if you have a watch, it probably has a little tiny cell. It wouldn't be very handy to have a watch with this big of a battery inside of it. Yeah, that's not going to be very functional. But again, you've always got a positive side and a negative side to every cell. This one is what it says on the label. We're getting 4 volts out of that, so it's very fully charged. Okay, so if all of these things in series multiply the voltage, what's going to happen if we have them in parallel? Let's take a look at that. We'll connect the ion battery. It's the way we keep a lot of charge for things like small devices. These are rechargeable. Batteries like this are not meant to be recharged. They can be, but the problem is they produce those gases and would explode. So we want to be very careful about that.
Do you know if those devices that they sell that supposedly recharge your dead batteries, do they work?
You should only use ones that are labeled rechargeable for those
okay.
types of devices. They're vented in special ways to allow those gases to escape and stay cool so they don't explode. So never put your regular alkaline batteries on a recharger. All right, so that's a little bit about how electrochemistry works. Hope you learned something about how we can use what God's created to bring us benefit in the world around us. So want to remind you again of our 20% off special we've got going with the website using the Matthew 6 code. And today we're featuring this book, The 10-Minute Bible Journey. It's written in a way that lets you walk through the Bible as a family, especially dads could be leading their families in these discussions and really thinking about the big picture of Scripture and how we've got that big redemption theme. And again, we'll be offering these live programs throughout the day. Today, Wednesday, we've got, you're going to be presenting a Q&A session?
Tomorrow.
Oh, tomorrow.
Yeah, tomorrow.
Okay,
Yeah.
Yep, tomorrow. And then today we've got Dr. Mortensen, Why Evolution, Creation Evolution, Why It Matters. And I think I misspoke yesterday. I was looking at the wrong schedule. So we have porcupines today. Yesterday was the horses out in the museum zoo. And then the walkthrough. I was looking a day ahead yesterday when I read those things. But thank you for tuning in. And again, I'll try to get some of the other questions if they come up in the comments. And we'll see you again tomorrow.